I'm here to welcome you to the S.J. Hall Lecture in Industrial Forestry. I think most of you know I'm Keith Gillis, Dean of the College of Natural Resources and a professor of forest economics. Before I introduce our distinguished speaker for the evening, Professor Ryan Smith, I'd like to acknowledge many family and friends from Berkeley and the communities to our north have been terribly affected by the devastating fires of the last week. It's been very difficult to watch at times as the magnitude of the disaster has become clear to those of us that are living to the south. Our forestry folks here, Scott Stevens, Bill Stewart, Rick Standiford, many others, they're responding as well, really, as we can in the forestry group down here to a lot of critical questions about how and why the fire could have spread so rapidly, caused so much devastation, and what can we do so that this doesn't become a new normal. And as wildfire protection, especially the protection planning dimension, is one of my own areas of scholarship and service to the state, I'm fielding a lot of those media calls myself. And if you've read or heard the comments any of us in the fire science group down here have been making, I think you'll probably hear a repeated message of how impressed we were with the resilience of those communities and how much we appreciate the outpouring of support that has come from around the world for the people that have suffered through this disaster. I think it's not surprising at all that a number of Berkeley students have been regularly going up to work as volunteers in the service centers for the evacuees. That says a lot about, what Berkeley students put into practice. They're not just talking about doing good in the world. They go out there and they do good in the world. And so also as the tragedies unfolded, I have to say I felt very honored more than once to be a part of one of the finest forestry programs in the world, but a program where a lot of the most important scholars in the field of wildland fire science act, work, think, and a program that has produced an awful lot of graduates who have just been outstanding in their roles as initial responders. In some cases, it's very sad when I hear of an alum that I know from the forestry program who's working in an agency like CAL FIRE and they've lost their home. But I know, they're doing what they wanted to do. They're out there and they're doing their job in service to the people of the state so well. So post-fire, CNR is obviously going to be involved in planning, policy, rebuilding efforts because of the deep expertise here that's relevant to the areas and to the general problems in fire science. And I think the fact that I'm already in discussion with members of the community down here and with the leadership of the agencies about, all right, what have we learned from this? What can we do? How can we not make this a new normal? And how do we respond to the suffering that's out there? I think that that's one of the reasons I always have hope for the future is every time I think things are rather bleak, I see communities like ours come together and say, okay, what are we going to do about this? And I really feel we will do something about this. And so let's all keep a good thought for all of those people that are hurting out there, both the people that were in the fire and the people that love and are related to them elsewhere. So, that said, we're going to move on to our lecture for the evening, and just a little background on the S.J. Hall Lecture Series and its namesake, Sherwood J. Hall. Mr. Hall got his Bachelor of Science in Forestry from New York State University in Syracuse in 1920, a program currently led by a Cal Forester. We're all over the place. He entered the forestry profession as a consultant in the South for the James D. Lacey Company, and in 1931 formed Forest Managers Incorporated, from which position he both managed forests and advised other forest landowners. One of those examples of interesting advice was when he had J.C. Penney as a client, who he aided in sculpting some fairly barren forest land into a beautiful forested retirement home. He played a major role in the development of industrial forestry in the South before he moved to the West in 1948. He's one of the first people in the California forestry community to recognize the potential of the West Coast young growth timber stands, right? We'd been in a period of exploiting the endowment of nature, and he was one of the people that looked ahead to say, well, this is a resource we can interact with in a sustainable fashion on an ongoing basis. Accordingly, Hall and two partners bought the 27,000-acre cutover redwood tract, establishing the Gualala Redwoods Company. And that company emerged very quickly as a leader in industrial management of young growth redwood stands and in the practice of sustainable forestry. Upon Hall's death in 1968, his widow, Mrs. Desi Hall, moved to create the Forest Economics Foundation to advance the understanding and practice of sound economic principles among forestry students. And forgive me if I'm biased to say that that is the most important part of the forestry curriculum, the economics part, and everyone needs to pay attention to that and really do all the readings. Later that year, she established the S.J. Hall Lectureship in Industrial Forestry and the S.J. Hall Chair in Forest Economics here at Berkeley. I had the privilege to hold the Hall Chair earlier in my career here, following in the footsteps of two of my mentors, Professor Dennis Teagarden and Professor Larry Davis. My friend and colleague Peter Burke then held the chair for a decade, and this year Professor Matthew Potts was appointed to the chair. And Matt can't be with us tonight. He's away on sabbatical. But, you know, given Matt's creative scholarship, his willingness to really get in there and be of service to the community he's part of, and his devotion to our students, I think he's a really great choice to pick up with the chair where Peter and I left off as we move into the senior phase of our careers. Hall felt that economic understanding is basic to effective forestry in a strong nation, and in keeping with that sentiment, we hold this annual lecture. And we're very glad to be able to hold the event and continue to support our programs and forest management, forest economics, and perpetuity, thanks to the foresight of Desi Hall. So I'd also like, before I move on, to recognize we have a member of the Hall family with us here tonight, so Susan Hall. Thank you very much, Susan, for the Hall family continuing to be interested in the program. We appreciate your presence. Couple announcements before we move on. After the lecture today, we're going to have a reception, and it was going to be outside, but we're going to move it inside because we had that little cloud burst last night, thank goodness. And so it's a bit moist outside. We don't normally plan for rain this early in the year, but that's the way it goes. We're very happy to get that rain. And so join us afterwards. There'll also be a private dinner later for the members of the California Alumni Foresters that are signed up for that and their guests. And we'll have you go up to the garden room where that is later and sign in, but we'll make an announcement at the reception. And after the presentation, we'll have a Q&A session. We have two runners, Catherine and Dominique, who'll be running around with microphones. And even though we all in the forestry community have voices that project boldly across two chains at least in heavy timber, the fact is an order of magnitude more people watch this lecture online than see it in person. And so using the microphone so that we actually capture your question and don't force the speaker to repeat the whole question so that the people watching it later can make sense is really great. So just raise your hand and you'll get a microphone. At this point, let's all recognize that We've all heard some interesting ringtones in public events recently, and let's turn this off. So, the real business. Our speaker tonight, Ryan Smith, is an associate professor of architecture at the University of Utah. He'll speak to us on increasing the value of underutilized timber through the development of innovative wood products for the construction market. He's the director of the Integrated Technologies and Architecture Center at the University of Utah. The center's researchers provide a range of expertise to industry, academic organizations, industry associations, and partners on research and development of sustainable building technologies, off-site modern methods of construction, prefabrication, and lean construction, optimization, energy efficiency strategies through passive design tactics. Really kind of the future of construction and the future of wood as a building material. Professor Smith's personal scholarship is in the area of architectural technology, focusing on enhancing integrated and sustainable design, as well as innovation into the built environment. He has numerous publications to his credit, a book on prefab architecture with Wiley. He's the co-editor of Building Systems by Routledge. He speaks widely in the community on emerging issues in the construction industry, like off-site building, building information modeling, integrated project delivery, sustainability. He's received a slew of awards for this work, including a number from the Collegiate Schools of Architecture, their Collaborative Practice Award, a two-time winner of their Creative Achievement Award. He's received the Architectural Research Center's Consortium Award and the Engineering News Record 20 Under 40 Award. So Professor Smith got his bachelor's in architecture from the University of Arizona. There will be some people from Arizona here this weekend. Hopefully they will go home very disappointed, but not our speaker. But after receiving his bachelor's, he migrated west to the geometric center of the universe, and he received his master's of architecture from our very own School of Environmental Design. So please join me in welcoming Professor Ryan back to Berkeley.
Thank you for having me, and thank you, Dean Gillis, for inviting me, and to the Hall family, thank you for having me. Appreciate it, and all of you for coming. Thanks to Dominique and also Renee for handling everything for me to come. Appreciate it, and Chris Ford, my good friend, is in the audience from Stanford, so thanks for coming. You know, coming back to Berkeley in this situation, it makes me feel a little bit like I snuck into the teacher's lounge. Right? So I'm not entirely comfortable up here, but I appreciate you inviting me. I grew up on a ranchette in Arizona. My parents were suburbanites who really had no business in running a ranch, but they decided with myself and my 6 siblings, a horse, a pony, 5 chickens, some pigs, and a dog, that we were going to have this outdoor experience. So I had plenty of opportunities to play, climb. Some of my earliest memories, like this photo, involved wood, nails, and building tree houses, and of course my rubber lizard. This is a photo of my great-grandmother, Nina Kleinman, my grandmother, Georgia Kleinman Wright, my mother, Linda Wright Smith, and the baby, my oldest sister, Tiffany Smith Coleman, in a 4-generation photo circa 1970. Nina, my grandmother in the blue, was a tenacious realtor in the East Valley of Phoenix, Arizona, in a town called Mesa. And she was a feminist trailblazer who was referred to as a firecracker by the barber who was giving me my haircut when I was a teenager. With her successful career, Nina designed and built a cabin in the lodgepole pine forest in northern Arizona. And this modest 3-bedroom, 2-bath cabin is where I spent most of my summers with my extended family, hiking, playing games, and of course, working. The cabin is a light wood framed with tongue and groove knotty pine wood on all the interior and exterior surfaces. Sometimes they were painted, and sometimes they were just clear lacquered. There's me, 1979. There's a story that my great-grandmother would come to job sites for her developments, including this cabin, and visually inspect the lumber delivered to the job site one by one to ensure the boards were straight and that there were minimal defects. She was, in her own way, a compliance officer, a quality assurance compliance officer. I have vivid memories of the touch and feel of this wood cabin and the surrounding lodgepole pine forest that enveloped it. Given the slow pace of these summers, the smell, the visual warmth, and the pattern of the grain of the wood evoked strong sensory responses that provided the emotional background for my future career. This past summer, my cousins and I met at the cabin to repaint the exterior. Lindsay, my wife, and I now take our children to the cabin every summer for a couple of weeks. As I mentioned, I'm a graduate of Berkeley. While I studied here, I was greatly impressed by the shingle-style architecture in Berkeley, which has excellent examples. It pervades throughout the Bay Area. This is a Julia Morgan that's still, of course, here. I think the ballet actually occupies this building. I also worked professionally in Berkeley at the offices of Bolin Sywinski Jackson, an architecture firm that now is in San Francisco. During that time, I was assigned to a residential design project called the Creekside House near Palo Alto. The client's primary concern was to preserve the large 100-year-old oak trees that stood on the property. A strategy to prop up the branches of the tree was designed and implemented. The house tucks under the oak canopy the house is framed and lined with timber. These early experiences were instrumental in forming an intuition and technical expertise in timber construction. And more importantly, however, as we are emotional beings, and I'm probably more emotional than most, as this is a sentimental beginning, this formed the beginnings of my strong belief that buildings should be wood. But why in the 21st century is it the time for timber commercial construction? The Industrial Revolution brought about standardization and mechanization. The blast furnace process allowed for iron ore to be smelted affordably, leading to the mass production of steel, from nails to large structural beams. Steel saws could cut logs, and laborers could nail together boards faster and more affordably than ever before. And light wood frame for single-family houses became favored above brick and stone masonry. About this time, the process for refining Portland cement, the binder in concrete, was invented in the UK. While wood emerged out of the Industrial Revolution as the material of houses, steel and concrete became the material of commercial construction, favored for their longer spans, durability, and what was perceived as non-combustibility. However, the consequences of the Industrial Revolution were not systematically considered or systemically considered. Ulrich Beck, the late German social scientist, suggests that we wrestle today with the side effects of yesterday's successes, that we are in a new phase of modernity today, in which our mode of operation, such as building, can be characterized by the development and implementation of contextual systems of increasing hazard. He says that our belief that society can somehow control the dangers that itself produces is self-defeating. While steel and concrete can certainly solve performance parameters of building, they have unintended, unknowingly environmental and social contingencies and consequences. We're all aware of the mounting social hazards. You've been a recipient of one most recently. There's also the tragedies in Texas, in Florida, Puerto Rico. Given the secondhand effects of the Industrial Revolution, policymakers and those in the building industry, like myself, are for the first time in my memory and in the study of history of building, seriously consider not only the operational performance of buildings, but the impact of the material selection on climate change mitigation. This awareness has propelled timber to the forefront as an innovative construction material of the 21st century among ecologically conscious owners, architects, engineers, and builders. This chart illustrates what I consider to be the socio-technical movements across industrialized history. The items in in red point to the positive social pressure that is moving timber into the commercial construction market. So we'll review a few of these if we look up at the board. The ones in red is ones I've kind of called out, what I think are pressures, socio-technical pressures leading to that. So we have urgent demand. Certainly post-recession pent-up construction demand is suggesting that we build a lot faster and in larger quantities, hence the use of wood. We also have the notion of systems thinking. In the second phase of modernity, the problems we created in the first phase, we're now suddenly thinking about them in a much more systemic way, hence the use of wood. We also have labor costs. There's a huge labor shortage currently across the construction sector. And therefore, we're seeing a lot of the operations happen on the job site being moved into factories in order to optimize that labor. That suggests that we build in factories, and in fact, wood is an easy material to manipulate through machines in the factory. That leads into this other issue, which is mass customization. Instead of thinking about standardization as economies of scale, like we had in the Fordist era, the 21st century is thinking about economies of scope. That means you can use one machine to do all sorts of operations at the same economy of scale. CNC robotics is pervading across the industry, but in wood in particular, it's become quite advanced. Digital design to manufacture, use of building information modeling to do that, which translates design software into manufacturing software, is becoming quite sophisticated. And of course, the sustainability movement, as I mentioned. And finally, and I think probably most importantly, we as emotional human beings are tied to aesthetics and other sensory components. And so I think one of the major reasons that wood is pervading is because architects seem to have currently a wood fetish. This is also dangerous because we had a concrete fetish in the middle of the 20th century. Where this will lead, I'm not quite sure. I run a research center at the University of Utah, as the dean mentioned. We focus on how buildings are built and the contingent social and environmental and economic implications of such. This has led us to wood and industrialized building as two primary topics. The center at the University of Utah is located in Salt Lake City, and due to the influx of high-tech companies such as IM Flash, Adobe, and yes, the US National Security Administration, coupled with the reality that much of the population stays in Utah and reproduces prolifically, the Salt Lake Valley is one of the fastest growing regions in the United States. For example, it's estimated by 2030, the number of housing units in the Salt Lake Valley will double what it is currently. Housing trends indicate that these 750,000 units that will come by way of low-rise multifamily apartments, condos, and affordable housing projects. This presents all kinds of planning and development questions, challenges, and opportunities, not the least of which is, how will these buildings actually be built? We explored the potential of construction materials that were currently not recycled or reused to perhaps could be used in that way. This brought us to the Utah State construction and demolition waste data. These numbers from 2008 demonstrate that concrete and mixed concrete rubble constitute the majority of construction and demolition waste in Utah by volume. Outside of crushing concrete into aggregate or pulverizing concrete into road base or road refines, it's really difficult to reuse. Metals, including steel, are already recycled nearly completely, nearly 100%. Wood is the only other structural material option that is currently in that waste stream. Research precedent indicates that there's a 0.5 yield on recycled wood, meaning that of the wood volume going into the landfill, by virtue of demolishing old buildings, only about half has historically been able to be reclaimed and reused functionally. But the literature only showed case studies of reuse for wood in finished applications, such as wood floors or cladding on the outside of buildings or wood lining on the interior. There were no examples of using it as a structural material. Even if wood is not recycled, such as using new virgin material, it really is the only rapidly renewable material that could be used as a structure. Wood as a raw material brought to use is a relatively low embodied energy material. This means that the amount of energy imbued in the material during the harvesting, processing, and transport is low compared to, say, metals. This is positive because energy in this country is primarily generated by coal-fired power plants, which presents a challenge for both pollution and CO2 greenhouse gas emissions, which has been linked to climate change. You can see that concrete is also a low embodied energy material. But that does not account for the carbon sequestration that occurs during the growth cycle of trees. Bruce Lipke, a colleague at Quorum at the University of Washington, has dedicated his life to working out life cycle assessments in wood. He's compared this to other materials, such as concrete. This image shows the net carbon emissions of wall assemblies, illustrating that wood is a net carbon sequesterer. Therefore, because timber has a low embodied energy, is net carbon sequestering, and can be reused and recycled, we became interested in a product that could take some of the deficiencies of construction and demolition waste, or underutilized wood in general, such as, and increase that capacity, such as its structural capacity or its durability, by reconstituting it in a value-added product. One product, cross-laminated timber, has been in existence for some 20-25 years, emerging out of the Technical University in Graz in Austria, developed by Dr. Gerhard Schickhofer. We could theoretically reuse waste wood in the construction demolition stream into this new product by glue laminating it into rafting layers, such as plywood, but using dimensional lumber sizes. But this presented challenges with the initial cost of glue laminated presses and the capital expenditure investment of large format planers and sanders that the wide majority of timber fabricators across North America do not have access to. Furthermore, there was a challenge of actually creating a wood reuse supply chain. We estimated that it would take an average of 13 homes demolished to create one from construction and demolition waste. That's a cross-laminated timber house. This is calculated both in mass and volume. So in any given year, the market would only be able to build about 600 to 1,000 homes from the construction demolition waste going into the landfill. This really didn't meet the demand of the 2030 benchmark in Salt Lake of needing to double its housing stock. In 2009, we learned of the mountain beetle problem in the Intermountain West forests. This was also a waste wood that, like construction and demolition waste, was an opportunity to make lemons out of lemonade, to add value to what otherwise was unused. Now, certainly beetle-killed pine can be used for biomass, but in our estimation, this is a lower value use of the product. We began exploring the opportunity to create a structural building product like cross-laminated timber, but at a lower cost for entry for timber fabricators that did not rely upon expensive machines, such as presses and planers. So I'm sure you're all aware, probably much more than I am, about the mountain pine beetle devastation that occurred. But just to remind ourselves, it damaged most of the intermountain forests. California was not immune to this. We know that the bark beetle infestations are exacerbated by longer mating seasons and warmer temperatures that dry out forests. Although the mountain pine beetle epidemic is slowly subsiding, according to Colorado State University, the spruce beetle is now kicking up. We estimated that the amount of forest infected in Colorado alone would produce over 2 million housing units. This is well over the demand of market for housing and could help to meet the rapid population expansion in the Intermountain corridor. Furthermore, we could aid in helping the Forest Service remove standing dead and create value for the forest sector. At the same time, Euclid Timber, a local fabricator located in the Provo Canyon on the back of the Wasatch Mountain Range, was exploring mass timber products. They were also logging beetle-killed standing dead material from local landowners' properties. They graciously invited us to participate in their R&D process and testing as a university partner, along with Brigham Young University and Acute Engineering, a timber engineer in Utah. Euclid Timber and its owner, Kip Apostel, who speaks German and is well connected to the Central European wood building industry, also owns a co-located Hundiger USA on the same property. Hundiger is the Rolls-Royce of CNC wood fabrication machines. In addition to having these tools in their shop, Euclid/Hundiger retails, supplies, and maintains Hundiger machines throughout the United States. The team developed a series of interlocking cross-laminated timber, or ICLT, wall assemblies from 2 to 5 layers, 5.5 inches to 13.75 inches in thickness. Like CLT, the system uses rafting layers of alternating beetle-killed pine lumber that are 3-inch thick boards that have been air dried to about 10 to 12%, plus or minus 2%. The boards are then tooled with a dovetail notch so that each layer nests into the next layer. The ICLT walls were tested at a pushover actuator test at Brigham Young University, and this served a number of civil engineering master's thesis projects. The walls perform similar to reinforced concrete for their lateral resistance, but have a large deflection. This would serve well in high seismic or wind zones, meaning it's safe for egress, but the finish damages occurring in the event would really cause a lot of economic problems, such as cracking of sheetrock, etc. The walls have also been tested at the USDA Forest Products Laboratory in Madison, Wisconsin, with the help of building physicist Sam Glass. The facility is known as the car wash. It's a weather and temperature simulator whereby the wall element is a mediating surface between simulated weather and interior environment. Sensors monitor relative humidity and temperature. The appropriate architectural detail is to conceptually capture thermal mass of the wall to the interior. We tested both vapor-open mineral insulation and vapor-tight insulation, such as polymer-based, expanded polystyrene, on the exterior surface. And our hypothesis was verified that similar to CLT, ICLT needed to have vapor open insulation to allow the wood wall to breathe. Furthermore, we discovered that while CLT with adhesives is able to resist air infiltration, ICLT without adhesives needed to add an air barrier. Without it, no amount of mass or insulation would matter in its thermal performance. Once the hygrothermal testing was done, a lot of these projects were built. And I'm just going to go through a few projects that have been built to date to show examples. This is a trucker barn. It's a funny story, a little bit counterintuitive, but a trucker who's on a major highway in Utah wanted to have a place where he could park his truck and live. And there's a golf course next door. So these are some of the hold downs. I hold down the wall panel, and you can see there's no posts, as you would see in standard construction where you engage a post. These are just drilled directly into the wall. There's no header over a window. You just place the dovetail joints in the layers or notches on the layers over those openings so they can span over large openings. You can see some of the trusses, and in this case, Euclid Timber developed what's called a dowel laminated panel for the roof, which I'll describe later. This is a project down in southern Utah near Moab called Rio Mesa Center. I served as its research director for a few years, trying to get other disciplines engaged. It's a biological and natural sciences research center. They have tents that you can stay in down there, but there's no bathroom facilities. And so we were charged with coming up with this idea. This was in partnership with an architecture firm and a construction company. Euclid Timber was able to fabricate and build this bathhouse, which holds 3 showers, 3 toilets, a sink facility. You can see it's beetle-killed pine. We then did a water-based clear lacquer on the outside so the wood could still breathe. And we actually furred out on the interior to house all the plumbing on the interior, but left the wood structural panel exposed on the exterior. This is an off-grid project, so all the water, solar hot water, and power comes through the roof. And you can stay there for $20 a night if you want to. So. It's in the Red Rock country of Utah. Project for the Girl Scouts of Utah. This was with Yor Grugemer and my colleague Yor Grugemer and Aaron Karaher, who were designers on the project. The idea was to engage the Girl Scouts in a meaningful activity so that we could increase our diversity in the Utah population among the building disciplines. It's a major issue for us. And so we engaged the Girl Scouts in the design of their cabins for their camp, and the girls came and participated in quite a few events. One in particular was called the Architecture Chicks event, and they all got t-shirts and got to participate in bringing their sleeping bags to our gallery space, laying out in them and seeing how they might occupy space by taping it off on the floor. We call this bricks and sticks, where they get to think about loads from a building and how wood might deflect. And then there was a panel discussion with some of the prominent women architects in our community. We took them to the Euclid Timber Factory, and the girls got to see how wood was manufactured and fabricated with the Hundegger machine. This is the design of the project, 3 cabins built to date. It's designed in CADWorks, which is a timber modeler. All the components and parts are designed that way, and then they're fed to the machine digitally, and the machine then cuts them. This is a little bit unique panel. It was a 2-layer panel, and you'll see how the construction kind of worked. This is a summer cabin, so it has no insulation. It's only used during the summer. The walls sit down on top of the floor through this dovetail joint. And then it's a little bit different twist. It's a bow tie notch that's driven across those 2 layers of panels. So you have 1, 2, and then it's driven across to, in that case, those are 3, but we have 2 and 3. Here's some of the architecture students visiting the job site. getting firsthand knowledge of how mass timber construction works. We did have some problems with pitch, but I won't go into that. So the wood was not, didn't go through a full seasonal cycle of drying, so we had some problems with pitch. It was just clad with a simple mild steel and a weather barrier between them. My son, when I took him to this project, he is a Boy Scout, and he said, "This is just not fair." You can see how many girls can fit into a cabin, and Aaron Carraher led a studio where they designed all the seating and tables for each of the cabin meeting spaces in the center. So the architecture students built those as well. Euclid Timber currently holds patent and license on the product, and this is their process. They now produce 2.5 width, what they're calling billets or blanks, and you can order them mass produced, and they stock them so they can supply them. ICLT is part of a family of glued and non-glued mass timber products. And so it's kind of an image we produced to explain it to people. On the top you have glued products, glue laminated timber, we're all familiar with that. Structural composite lumber, which could include LVL or PSL, and then cross-laminated timber. On the non-glued side, these are less familiar to people. Product that came out of Germany is called dowel laminated timber. You dry the hardwood dowel down to a very low moisture content compared to the base wood that it's accepting. You drill through, and then when that the ambient relative humidity increases, that dowel expands and locks the panel into place. This is called nail laminated timber. Similar concept, stacked planks, and you nail through them, usually with aluminum nails. Cross nail laminated timber is the same, and that's because then you put it on a flatbed machine, and you can CNC cut windows out of it and just go right through the aluminum nails. And then the ICLT is the product we developed that has no mechanical fasteners or glue. Currently, there's about 40 CLT plants that dot Central Europe. There's only 2 producers in Canada of CLT, and we have 2 in the US with another 2 that are being planned currently. Dowel laminated timber. I don't know how many are in Europe, but in North America we have 2 producers, Euclid Timber in Utah and Struck Craft up in Vancouver. There's a couple of nail laminated timber producers as well. Hundigger owns the patent on cross nail laminated timber, and they have a specific machine they produce. And there are about 20 plants across Central Europe that just produce C and LT product. If you aren't familiar with cross-laminated timber and where this is going, this is the 18-story project just finished in Vancouver that is built out of a hybrid. It uses glue-laminated timbers for the columns, posts, and it uses cross-nail laminated timbers for the floors. And this went up 18 stories. You can see how fast this is. We're in week 2. This is incredibly quick. So this is the reason people are going this direction. This product comes out of Structural Lam, located near Vancouver. This is built for UBC, University of British Columbia. I just got an opportunity to see it two weeks ago finished. It's pretty incredible. Not just is all of this prefabricated. Those 2 stair cores are site cast concrete. That's where the elevators and stairs go. That's for lateral resistance and also fire resistance. And then the whole exterior is a prefabricated cladding system that has embedded windows in it. I got an opportunity to interact with the superintendent on this project, and she had some great stories to tell. It's highly collaborative between all the players in the project to make this happen. I think there's a 17-story project being planned for Portland right now by Lever Architects, and so we'll see much more of this in the US. We were interested in this product CLT from a kind of research market study perspective. So we took 17 projects, spent 3 years, and documented how they performed, solid mass timber projects, how they performed, and we compared them against like-for-like developed a system with Cummings Corp, who's a cost estimating firm out of DC, like-for-like projects with these projects. And what we were able to then compare is how they compared in cost, how they compared in time to speed to delivery, cost per square foot. And what we found across this, for example, Bridgeport House in the UK was 7% more cost effective than what the industry is building and 25% faster build time. We then broke it down into a number of parameters. You can see the schedule, you can see the number of stories, you can see the amount of square feet. So it does perform quite well. The caveat or the limitation in this study is we talked to building stakeholders, architect, we interviewed the architect, we interviewed the fabricator of the CLT, and we interviewed the general contractor to try to triangulate the feedback. If you had a project that went under and did not do well, would you share information? So this is the challenge we had, is we got information that we had available. Across all those projects, we found about 11% average cost savings, better on construction costs, and 20% schedule advantage. We then went to developers and said, if you had a project that came in 25% faster, or you had a project that came in 50% faster, on your general conditions for your construction project, how much money would that save you? And we were trying to convince developers, go this direction, use wood mass timber construction. And so you can see there is some savings. So we had $52,000 in savings here, $76,000 savings there. On two different projects we looked at, a retail space and an office space. Across the market, I mentioned labor is a challenge. And right here, we see that out of the recession, we have construction volume is up. It's up at the level of pre-recession. So we're building a lot right now across the US. But the labor that's available to meet that demand is just not there. It's because it fell out during the recession. So for instance, the architectural profession is estimated to be some 15% lighter out of the recession. What this means for the production of buildings is that we need to bring operations more and more into the factory in order to optimize that labor. Currently, what's called the off-site construction sector, or the industrialized construction sector, is estimated to grow from 3% of the market to 5% of the market in the next 5 years. Two other products that are emerging that I think are opportunities for wood. One is Panelize construction. It's been around a long time. It's essentially to make a wall panel as you normally would on the job site, but do it in a factory. These can be anywhere from 8-foot lengths all the way up to 40-foot lengths, depending on your need. In Scotland, this has been perfected. About 75% of all their multifamily housing is built this way. So you can see they design it in the computer. It goes over and automated nailers put the wall together. There's a butterfly table that you finish one side and then flip it over and it finishes the other side. You can even put a stucco finish on the outside, and then they're craned into place. They're building buildings like this, handsome, well-designed buildings with brick veneer in the factory. Just show you a single-family house that's being built with panels, and I'll just show you the first day. That's the porch deck. Siding is already on. Spray foam insulation on the inside. This company is called Landmark Group. Their sister organization is called AccuBuilt. They're located in Edmonton, Alberta. They're the most sophisticated home builder in North America by far. They use all machines out of Germany, fully automated line, and they produce 6 homes a day. The most expensive portion of off-site construction in any regard is the crane. So the longer you keep the crane on the job site, the less money you make. And so as many lifts as they can get with that crane, they will. And then they will move that crane down in a production development like this in order to use it on the next house. There's a floor. This is all one day. This has been done in Sweden for decades. Post-World War II, they started building this way, and they've just found great efficiencies in doing it. So you cannot buy a home in Sweden that is cheaper site-built than factory-built. And that includes architecturally designed homes. The goal set forth by Sweden post-World War II, because of their horrible weather, is you want to get dried in one day in a house. So the goal is not to have any weather encroach on the interior of the home. So that would disrupt the wood, right? And it would cause it to warp. We don't seem to care about that in North America, though, so much. So big modular roof chunks with shingled on the top. I really do believe this is the future of industrialized building. That's day one. This is called modular construction or volumetric construction, as it's known in the UK. Not to confuse it with mobile homes, right? So this is built to IBC or standard code, building code. You build a box with all the sides, all 6 sides, and then you can stack one on top of another. That's day one. We did a similar project to the mass timber study in which we took 17 permanent modular construction projects and we compared them to site-built or stick-built projects. The ones underlined in red were built in wood. The other ones were in steel or concrete, still modular, but built in other materials. But what we did find is across the board, we had an average of about 11% cost savings. And we had an average of 42% schedule savings. It's incredible. It's not uncommon to hear that construction is delivered in half the time with these projects. We were very interested in all 3 of these technologies. Panelized, modular, and then standard built. So we had FP Innovations that approached us and said, would you do a study to compare prefabricated wood methods for standard multifamily housing, which is going to dot the Intermountain West and all across the West. No podium, just wood built from the foundation all the way up 4 or 5 stories. So we took standard projects called the Bud Bailey Apartments by Method Studio Architects, partnered with them, and they gave us all of the data and the BIM model, and we set up spreadsheets and algorithms to determine how much wood volume is being used in the project. We then wanted to model it in panelized and then modular and compare how much more or less wood volume is used in those projects. What we found that for softwood only, that's lumber, dimensional lumber, standard stick framing on site was 2.43 board feet per square foot, panelized was 2.74, and modular is 2.88. So modular has an increase of 19% wood. A Weyerhaeuser would think that's a great idea, right? So I'm sure they're going to do a Got Wood campaign really soon. Got Prefab campaign really soon. So where do you make up the difference? Where do you make up the cost difference? It's in labor, right? That's really where the cost is. So any time you can reduce labor, that's where the majority of cost is saved in construction. We then looked at total wood, including engineered wood, so both softwood and engineered wood. In modular, there's a significant amount of LVL that is used for rim joists. That's the wraparound on the outside. And because each one is a box, we found that it used 69% more total wood than a standard stick frame building. We're now taking this and looking at carbon calculations, because we know that wood sequesters quite a bit of carbon, and seeing what the environmental benefit might be of using wood compared to site-built. And we're also doing a cost analysis based on this as well. I want to end with this. What are the opportunities for the wood products industry? Here's the major ones I had on my mind in the plane this morning. Okay? Number one, there's significant capital investment in prefabrication currently. Marriott Hotels just announced that 15% of all of their mid-rise or their low-rise product, think Spring Hill Suites, Fairfield Inn, all of that is going to be modular this year. Most of it built right out of Boise, Idaho, here in the West. Amazon, Facebook, and Google have all announced they're going to use modular in their housing projects. Katerra, which is a company in Phoenix, if you aren't familiar, you should look them up. They have a $250 million investment. They have grown from 8 to 850 employees in 2 years, and they're one of the premier multifamily housing builders in the West. They're fully vertically integrated, with architects all the way through to closeout. Factory OS just announced today on Google, you can look it up, that they are going to take over the old Blue Homes Vallejo factory right here. And they are partnering with the Turner Center and the CED, and they're going to be exploring options. I don't think the machines will be in until December. I think that's an opportunity for this college to engage with research. Detail and specification standards. I'm working on a project with Arcom Master Spec, who is the American Institute of Architects publisher of their specification system. And they are now going to be developing a wood modular specification specifically for that, because it's growing so much, and there's no standard in the industry. So that's a big opportunity. Industry incentives. Edinburgh Napier University is an incredible leader in taking wood as a resource and increasing its value. They do a number of projects. I spent a year there on sabbatical. Dr. Robert Hairstons worked on a project called Wood Pig, Wood Products Innovation Gateway. Great name, right? What they did is they looked at the full supply chain from silviculture all the way through to closeout and construction projects and asked, how can we create value with wood products? They developed a number of new products with factories and university partners. A great idea, investment from the government. I could imagine that California would want to do something like that. Canadian subsidies. When Canada wanted to get started on their CLT initiative, they invested heavily in all sorts of subsidies, not only for the forests, but the transportation in the forest, transportation companies, the mills, et cetera, all the way down the supply chain in order to get that capacity going. Seattle, Vancouver have wood first initiatives. When you submit for permit, you have to demonstrate why it's not wood in order to get passed, okay? So they have initiated that as their effort. Oregon, as you know, the big effort in Oregon with the center there, they have invested heavily as a state into building capacity between factories and universities. Regulatory pathways. CLT is now in the 2015 building code. That has been overcome. Ironically enough, in Europe, it was used for 20 years, and they still don't really have it in the building code, but it continues to pass in a special structures section. But we do have it in the building code. We just need to increase demand. Type 5 construction, which is light wood frame, is going 5+ stories, and that push in Canada to get the code to accept that is happening. So we probably see 6, 7 stories here soon. And then you're familiar probably with AB 262 in California, which is the environmental regulation that just came out, and I think that's going to push in the direction of wood because it's a low carbon material. Software tool development. Autodesk just announced last week that it just launched a new prefab tool. So they are going in this direction. And there are multiple architecture, engineering, construction hackathons across the country in cities where they come and try to write software for timber fabrication. Finally, wood has not traditionally been a material that is taught well in architecture and engineering and construction management schools. So one thing that I've been trying to do with partners across the US and in Europe is to develop exchange programs where we have students that spend time in different schools. We're also trying to exchange laborers from one company to another to share knowledge and information. Finally, I've developed this Twitter, #ShouldBeWood. Anytime you see a steel building or a concrete building that should be wood, take a photo and post it, okay? Thank you. I think we'll do some Q&A if we want to.
You were mentioning the deflection in these cross-laminated timber panels. Are you referring to the glued or the unglued panels?
Unglued, the one that we developed, yeah.
Okay.
Glued is fine.
Yeah, it seems to be something that should be very rigid if it's glued. How about the increased use of timber, especially with the Title 24 requirements in California now? They're calling for extra thick walls in certain climate zones. That's going to call for a lot more usage of timber, and wouldn't that increase the prices of this raw material?
So maybe I can back up and just say, from the perspective of energy performance, what's happened in Austria in particular is CLT has become synonymous with what's called Passive House standard. So Passive House is a very aggressive building standard. It's voluntary, but it is solely based on energy performance. And that's because you get a really tight envelope for air infiltration with CLT because of the glue. So they're able to do that and then put the insulation on the outside and get their values pretty easily compared to a cavity wall, whether it's a steel cavity wall or a wood framed cavity wall. So I think from that perspective, we do see locally the Passive House Institute in the United States pushing for CLT because they see it as an energy performance measure. And the added benefit is that you get low carbon, right, in the building material. So that answers part of the question, but I'm not quite sure how to answer the question about cost increase. Yeah.
Two questions. One, is there any limitation on species with respect to using CLT? And kind of a follow-up question, is there any limitation on diameters, i.e. small roundwood, which is a major problem in California?
I do know that they're using small diameter trees for CLT production. And what that means is each lamella, each layer has to be quite a bit thinner, right, in order to get that done. But they are doing that. As far as the limitation, I'm not sure what that dimension is for the diameter of that tree. And then your first question was regarding species. There's been all sorts of species used in CLT. What is generally thought of as a value-added enterprise is to take a low-grade species, right, such as beetle-killed pine. So you use pine and then low grade of pine and use that in the tree in the wall in order to add value. But I've also seen people experimenting with hardwood CLT. That's being looked at. But I don't think that would be a value add personally. But, yeah, does that answer your question? Yeah.
Hi, and maybe you said this early in the talk. I wasn't here for the first about 10 minutes, but I was curious about the sourcing of the wood for these products. Are we looking at virgin timber in the boreal forest? Are we looking at tree plantations? Because that affects the environmental footprint as far as carbon sequestration. Yeah,
you're absolutely right. So I do know for, say, the project in Vancouver at University of British Columbia, that's all virgin material. That's all new growth wood. For the projects that we're working on, these smaller, what I would call demonstration projects that we're using with Euclid timber, those are all going into private lands, clearing out the beetle-killed pine and using those logs. So that's a very sustainable process. I've had a lot of people say, great lecture, Ryan, but what happens if demand takes off and we have to use all virgin timber for this? My argument is that through sustainable forestry, my gut feeling, and I need to do the research on this, is that it's still a more sustainable way to build than to build in concrete and steel. So, life cycle wise, I really believe that, but I'd have to prove that out. It's a good question. Yeah.
In the presentation, you concentrated on trees that needed to be removed anyway. And my question is there a prospect for a landowner to actually have a net value added at the stump, or is it all value added at the factory?
Good question. I don't know the answer to that question. And I also, it's very apparent, I'm not on the economic side of forestry, right? I don't understand that. I probably understand it as much as I understand our healthcare system in the US. So I couldn't answer that. What I do know is that in order to get CLT into market, the factories have to make money, right? And so we're trying to find ways to make them money so that we get more wood produced. An architect or an engineer can specify timber all day, but if there's no supply chain, they can't deliver it. So.
In terms of fire performance with the CLT frames, are we looking at a closer performance to like heavy timber frame, or is it still working in terms of a Type 5 framing system?
No, you can get a Type 3 construction with it if it's sprinklered. And frankly, unprotected steel is a lot worse, right, than mass timber. There are many fire tests that have been done and proven out. And one strategy that they're using, especially for high-rise, is to have a composite panel. So you have a CLT floor with a 4-inch concrete topping. Yeah.
Do you think that catastrophes like the North Bay fires are going to change or make people more hesitant in building with wood because of the perceived vulnerability of it as a structural building material?
I think perception is one thing. I think reality is something else. I don't think it's any more of a hazard. If you have a raging fire in a forest, a house in concrete is going to burn just like a house made of wood. Not as bad, but it still will. That's the misnomer is that, I mean, we just sprinkled a fully reinforced concrete building at the University of Utah for our School of Architecture. And you say, why would you do that? It's because they still catch on fire. Now, a lot of people have said, well, we should start building our houses in concrete and masonry again because of fires. And I would say, I don't think so, because we have an entire market that is oriented at wood. And to think that we can push a market to something else I think is a big stretch. Now, could individual states lobby and go in that direction? The concrete lobby is extremely powerful. They somehow were able to not be in the new environmental regulations for California. So they're very powerful, and they are, so I know a lot of them. They're petrified of the timber industry right now because it's going to eat into their market. But to answer your question specifically, I don't think it's of worry. I think the challenge should be us finding ways to protect wood, to continue to use its benefits, but overcome the fire challenges. And like the composite floor I just mentioned, these are methods that are being developed. So, yeah.
So Ryan, as part of your argument for this modularity is that with the wood, it won't be so butt ugly as the typical modular construction we see. There's a lot of examples of modular construction that are really ugly.
Yeah, sure. Modular is only good as the demands placed upon it by architects, frankly. And so, unfortunately, I think we've had a lot of early examples of undisciplined architects using it to get a project done quickly. Fortunately, the new factory OS that's been developed, the architectural partner there is David Baker Associates, which is a great architecture firm out of San Francisco to do affordable housing. So I think you're going to be seeing it used in a very smart way very soon. And then there's some great examples in New York that have used it, not in wood, but in steel. And so it can be done. Gluck Plus partners, shop architects, these are very sophisticated designers that have done some great things with the product. So.
Yeah, so pardon, I am an economist, but watching these construction videos and the timelines they're covering and thinking about the question of building with wood, we've had several instances in the Bay Area recently where the extended construction period of a building with a lot of wood in the framing, tremendous investment, months of construction, and then the thing goes up in a big fire.
In a fire, during construction.
Right? Yeah. During construction. Yeah. The speed with which this becomes a shell and a more controlled access environment, and the nature of the materials that you're moving on site relative to what's on site in a traditional construction. Is there a potential cost savings in terms of the insurance cost in, say, a large apartment complex that could factor into this ultimately?
That's a great question. There's a lobbying effort from the Modular Building Institute, which is the trade association for modular buildings. They are material agnostic, to try and push for this kind of thing, and specifically for worker safety, right? So I keep laborers off the job site. I've also all of a sudden increased the safety of that project considerably. I don't have to hold as much insurance. That's a benefit to my general conditions as a general contractor. I think we're seeing large contractors like Turner Construction or the big ones, DPR, kind of moving in this direction and saying, yes, we already see the benefit. So I think it's going to happen. Yeah.
What I didn't. What I didn't quite see when they put these cross-laminated panels is how you design chases for plumbing and for wires and where do they fit. And I guess also if you go to colder climates, do you put in some extra layers of insulation, or how do you deal with some of the technical issues of that?
Yeah, so insulation is usually put on the outside of the building, and it's actually a really good way to insulate because you get no thermal bridges. Right? So it's a complete seal from the environment, so that's a benefit. Still get breathability of water vapor because it's mineral wool insulation or wood fiber insulation. You wouldn't want to seal it down like a plastic bag, but you do get that from that strategy. As far as wires and things like that, you do have to accommodate for those in one way or another. And usually the way that's done is you build a small wall on the inside surface with furring strips or smaller members, and then you route your wires through that. The incredible thing about these CLT buildings is I've seen 3 projects in which they've shown the waste at the end of the building, right? At the end of the build, when all the timber is up. And it's like a bucket full of sawdust. That's it, and maybe some screws, that's it. So it's put together with metal brackets and screws, standard wood screws. And to think that you could build a steel or concrete building like that is ludicrous. So just from that standpoint, it's just, it's incredibly beautiful. And then they tell stories of these crews that go up and recite a poem at the end to the tree gods or whatever, and then it's over. But right now we have a lot of demonstration projects, and I should say in the last 5-10 years, what we're finally seeing just in the last year is that mainstream projects are using this. These are not owners that are totally sold on the environmental benefits of wood. They're actually real projects that are bottom line about first costs, and they're finally using the product. So what that means is the fabricators are able to come in with bids that are very competitive or at the same cost as all these other products. It's exciting to see.
Yeah, question, could you comment with respect to CLT building and what's going on in the nanotechnology cellulose area? And is there any overlap between using nanocellulose for glues or structural support?
Great question. I just Googled Google Scholar yesterday asking that same question. I didn't see anything. So I don't think there's anything out there right now. Yeah, it's a great question. Yeah.
What percentage of architectural firms in California would you say are looking at mass timber as an option and pushing that with their clients?
Oh, that'd be hard to say. So I lecture on this topic quite often. And I'm out in the community going to architecture meetings and things like that. I have not met a person yet that doesn't know what CLT is. I mean, it's pretty well known. And their projects are winning awards, and so they're fairly familiar with it. Do they have the technical expertise? Absolutely not. So what they've seen is glossy images in a magazine, and they said, yeah, we should look into that. But I do know that there are construction firms and architecture firms in the Bay Area who have invited experts to speak. We were just talking about that at lunch. Michael Green is a CLT architect up in Vancouver, and he's spoken locally here at closed lunch meetings. So there are firms who are seriously considering it. Yeah.
I just wanted to point out, to continue a point that someone else had made earlier, that a lot of communities are requiring sprinkler systems in new homes anyway. Yes. And most of these new homes, of course, are timber framed. And also the concrete structures, high-rise buildings made of steel and concrete have lots of furniture, drapery, carpets, and the plastic insulated wiring. All of these things can burn. And we've seen a lot of catastrophes where the the steel structures soften as the temperatures increase and then it just collapses. So steel and concrete is not the answer, but if wooden houses do burn, they actually stay up longer as the fire progresses, and that allows people to exit or more time to exit safely.
Thank you for your comment. Is that it? I think we're good. Thank you so much. Appreciate it.